Hello, everyone, and today's topic is volcanoes, and a topic that tends to be everyone's favorite. Volcanoes, besides being extremely cool, they're very important. They're important because they're a good follow-up to last week's topic, which was igneous rocks. And as you know, igneous rocks are formed from the solidification of magma or lava. Now, lava comes out of structures called volcanoes. But volcanoes are also important because they've helped us glean a lot of information through geologic time as geologists are studying it. Volcanoes are essentially a way for material transfer from the interior of the earth to the exterior of the earth. Now, that's not to say that we can't get volcanoes that are not associated with the plate boundary. We definitely can. We can definitely get intraplate volcanoes. But widespread and extensive volcanoes tend to occur along plate boundaries. Now, why is that? If we go back to when we discussed in igneous rocks how we create melt in the first place. Now, remember, melt is essentially if you were to take an igneous rock and push it into some kind of fluid form. Igneous rocks form from a melt in the first place. Now, there are many different ways in which this melt can then cool into an igneous rock. It can either cool deep down inside of the earth very slowly and create what we call intrusive igneous rocks, or it can cool fairly quickly, and we call that extrusive igneous rocks. The reason why volcanoes are generally associated with plate tectonic boundaries goes back to how we create melt in the first place. Remember, melts are created in three main mechanisms. Those are through decompression, or the releasing of some kind of pressure. Those are through heat transfer, or they are through the addition of volatiles. Now, the three mechanisms in order to create a melt, those are all associated with the different kinds of plate boundaries and also hotspots. The interior of our Earth is extremely hot, and we know that. The reason why the interior of our Earth is extremely hot is due to two main reasons. It is what we call heat that is essentially left over from the formation of our Earth, and we call that primordial heat, but also heat that is being generated due to radioactive decay, and we'll talk about that later on in this semester. Even though the interior of our Earth is extremely hot, it doesn't mean that there are just many pools and giant oceans and lakes of magma that reside in the interior of our Earth. It is far from that. A majority of the interior of the Earth is almost in a solid state, or solid-ish. It's not in that melt state. Now, the base of the crust, essentially that boundary between the lithosphere and the asthenosphere, the base of the lithosphere is hot enough to where it can start to melt parts of the mantle. But the reason why it doesn't, generally speaking, is because all of that solid rock at the base of the mantle, even though it's very hot, is under extreme amount of pressure. So all of those molecules that are trapped inside that solid rock have nowhere to move. At the temperature that those rocks are at, if you were to drop the pressure just a little bit, enough to the point where those molecules essentially had a little bit more wiggle room, you could begin to create a melt. And that's exactly how we can go from a solid rock to a magma in the first place. And we call that decompression melting. Now, decompression occurs when we release the pressure. And generally speaking, the areas on the Earth where we can release pressure are generally associated with plate tectonic boundaries, those being mainly divergent boundaries. So something like a mid-oceanic ridge or a continental rift, where we know that the lithosphere at those areas tends to thin out because you are separating that plate there. High temperature, low pressure, we can begin to create a melt. Now we have two more ways that we can create melt. One is through the addition of volatiles, and one is through the transfer of heat. The other type of mechanism to create a melt is through the addition of volatiles. Now, volatiles are gases that want to remain in their gaseous state, at atmospheric temperatures and pressures. Addition of volatiles tends to occur at subduction zones, where that subducting slab, as it's getting swallowed underneath the overriding slab, that more dense and cooler subducting slab will trap volatiles on its way down, where those volatiles can actually begin to break some of the chemical bonds that are within the crystalline structures of the minerals that are within those solid rocks. Because it begins to break some of those chemical bonds, it lowers the overall melting temperature, the melting point of that solid rock, and thus it can begin to melt at a much lower temperature. The last style of creating melt is through heat transfer, and that tends to occur at hot spots, where you have some kind of magma chamber that is bubbling and boiling that begins to heat the overriding crust. Now, the reason why I'm talking about the mechanisms to create a melt is because the material that's ultimately coming out of a volcano is melted rock. Now, melt that is created through three of these mechanisms has two kind of pathways of cooling. Either it will stay there in that magma chamber and cool slowly through time, or some of that melt will slowly make its way towards the surface through what we call a conduit, which is essentially a path from the interior of the earth to the exterior of the earth. A lot of these times, these conduits lead to volcanoes. And as these conduits begin to grow through time, they will continually allow the transfer of melt within the interior of the earth through the exterior of the earth. This is a pretty good schematic diagram of a cross-section of a volcano, where you have the stylized magma chamber in its basic sense, the conduit, which is essentially the pathway in which the magma will slowly make its way towards the surface. You have the vent, which is where the magma that will then breach out from the interior of the earth to the surface, where then it will spew over in the form of lava. It is important to note that this is a very illustrative example of a magma chamber, where when we create melt, it doesn't just form in these poolings deep down inside of the earth. More likely, when this is more likely to occur, where you have solid pieces of rock, those pore spaces will then be filled in with the melt. So a majority of these magma chambers, for the most of the part, are solid rock, and is only a really small fraction that is the melt in its fluid state. Then you also get a little bit of gases that are also in the mix of there as well.